All right, let's get into designing our shear reinforcement. Up until now, we've talked about how much we can expect from the concrete, which is 2 square root F prime C BWD for the most part. That's assuming there's no axial tension or compression. And then if you don't have it, if you have between 1 and 2 square root F prime C BWD, so that's half of your concrete strength up to all of it, you only have to provide AV min. But if you have more than that, you need shear reinforcement to make up for the strength that you need. And this is how we calculate our shear reinforcement. This is according to 22.5.8. It's on page 410. Right? There we go. VS is your area of steel in shear, the yield stress of that steel reinforcement, depth to your tensile reinforcement, and then the spacing. So let's see, AV. Is your effective area of all the shear bars or wires within a spacing S. You can see the spacing, right? That's your distance center to center of your shear reinforcement. FYT is the yield stress of your shear reinforcement. D is what it's been before. Distance from extreme compression fibers to the centroid of your longitudinal reinforcement, right? We're talking about D. Like I said, it hasn't changed. It would be, like that, right? Positive bending. S is the spacing of your shear reinforcement. Now really, you can kind of break this down into the contribution from your shear reinforcement is your area of shear divided by the spacing times Fy times D. The key, what we're going to be looking for is this. And if I look at the cross section itself, right, we have, well, let's remember what the crack looks like, right? We got like a 45-degree angle crack. And we want to know in the plane of the crack, so in and out of the page, how much shear area we have. So if you look at like a cross section, if you look at like a cross section, let's say that's a number 4, right? Your area of the crack would be somewhere, oopsies, like going across your cross section. The area of shear resistance is AV equals 2 times the area of a number 4. So 2 times 0.2 inches squared. If you had a slightly different setup where you had, let's say there's a 3rd bar in there, and you draw your little crack, let's say it's number 4 and a number 4 tie. So now you have 1, 2, 3. So your area of shear reinforcement would be 3 times the area of a number 4. So 3 times 0.2 inches squared. Right, and that kind of goes back to, you can see here, oops, let's make that a prettier color. What is providing your shear resistance is your concrete contribution, right? 2 square root F prime C BWD, and then your AV times FYT. And it's over a distance D at a spacing of S. That's where they get this formula. AV over S times a length D. Right, so kind of stare at that picture a minute. Your steel contribution for shear is over this 45 degrees, right? A depth D from here to here. You're gonna have so much AV, shear reinforcement, over a spacing S times a length D, and multiply it by your yield stress. So that gives you a force, right? That'd be basically saying 1, 2, 3, 4, maybe 5. There's 5 bars over a length D, and that's why you have the D over S. If you have, so just, this is, we can put it up here, but the limit state that they use for shear is limit state of yielding of shear reinforcement. That's why we use the yield stress. This is assuming vertical reinforcement. If you have inclined reinforcement, that equation is just below. The other one, now you have to multiply it by sines and cosines. Now my equation, if I have inclined reinforcement shear stirrups instead of vertical ones, my contribution from my reinforcement is AV over S FYT times D times sine alpha plus cosine alpha. the same basic equation, you're just translating it into sine and cosine. So my angle alpha, right, you can see it right there. Angle the angle between your inclined stirrups and the longitudinal reinforcement, or the longitudinal axis of your beam. And your spacing S is still, you notice it's still actually horizontal, right? Or in this case, it's parallel. It's not that, right? It's not that. There's also some recommendations on sizing. I'm looking at 25.5.1.2 on page 402. Cross-sectional dimensions shall be selected such that your shear right, your BWD let's see, VU, right, this is page 402. This part right here, right, it would be VC plus VS. That means VS maximum, the maximum contribution from your shear reinforcement is 8 square root of prime C B W D. that limit state is excessive inclined which are typically associated with shear inclined crack widths. Basically, if you have to size it so that you're not gonna just crack all of your beam. And it's just basically hanging out, being held together by the steel cage of your shear reinforcement. If VC is 2 square root F prime C B W D, I'm going to put that in there. Then this simplifies to just 2 plus 8, right? 10. So if you're sizing for shear, you need to size it so that at least you have BWD 10 square root F prime C times phi. So this is all in chapter 22, which is about strength and serviceability, particularly the part about shear strength, right? Earlier in the chapter is about flexural strength, and axial strength is in there too. We'll get to that in a minute. Now, we've talked about AV min, but we also have to talk about other reinforcement detailing. So this is chapter 9. I'm on page, let's see, 9 point, right? Chapter 9 is all about, what is this? Beams. And reinforcement limits is 9.6. And then I need to be better about talking about what, because it feels like we're all over the board, right? Reinforcement limits is in chapter 9, and that's where we have our flexural reinforcement AS min, and then AV min, which we just talked about. And if you go to 9.7, you're talking about the details of that reinforcement. right? That's where we had our minimum spacing discussed, and more detailing with tension reinforcement that we haven't gotten into, with how long stuff needs to be. Still in. Now we have transverse reinforcement. That is shear generally, right? Shear. If required, shear reinforcement shall be provided. If required, shear reinforcement shall be provided. Right, I'm on page, what page is this? 146. If required, shear reinforcement shall be provided. Right, we figured out whether it was required with the AV min or if we need supplemental strength. Now we got to provide it using stirrups, hoops, or longitudinal bent bars. And then this table says the maximum spacing and how far apart they can be. So this is on page, oh, I have it tabbed. Page 147. If you need 0 to 4, so this could be AV min. This is where if you need AV min, you're looking at that first. It could be that one. Yeah, because if you this means, yeah, if you have AV min or you need less than 4 F prime C BWD, then your maximum spacing, obviously we're not looking at pre-stressed. Your maximum spacing along the length of your beam is the lesser of D over 2 or 24 inches. If you need more, then your maximum spacing is D over 4, getting closer together, or 12 inches. And again, this is if you're looking along the length. So this is how far apart you can space them. If you go to 25.7, which is page transverse reinforcement requirements. Oh, I'm in 22. I was like, Why is this talking about torsion? 25.7. We haven't been able to get into development length, but yeah, I'm on page 494. So we haven't been able to get into splices and development length, but basically it takes a while for it takes a certain amount of anchorage for reinforcement to develop its length. It has to be bonded to the, it's not like it has a full length, like just right where it's connected to the concrete. You gotta go out a little ways. So that's why this says, again, it's on page 494. Stirrups shall extend as close as you can to the compression and tension sections requirements as cover requirements allow. And then the reason it says it is essential that shear and torsional reinforcement be adequately anchored to be fully effective on either side of the potential inclined crack. So what I just wanted to write here was in a smaller pen size. They have to be anchored within the compression zone. To develop their full yield strength. And place, that means place as close as you can. Right, so that's why, right, this is like my compression zone right here. I'm anchoring it, especially with that little bend right there, helping to develop its length, or helping to develop its strength, not length. And so that's why usually when we do, we go right to the cover right to the stirrups and then to the longitudinal reinforcement, because we have to develop that strength of our shear reinforcement. This is the limit state. Failure of shear anchoring. Right, if you only started your shear down here, it might just pull right out. Or it might not have that yield stress that you're looking for. Just some other things. These are in the book and they're fun to look at. Right, this is our stirrups, as close to the faces as you can get. That allows the development. You always have to have a longitudinal bar in each bend, even if it's just minimum. This would not be allowed if you had something that kind of looks like an I-beam, or maybe like a barrier or something, like a jersey barrier. If you had that cross section, let me see if I can draw it. Tension in the stirrup would straighten it. So instead you would put reinforcement like that. Not bend it like that. Again, you have to have a longitudinal bar helping it stay in place on the inside of that bend. Finally, our last topic is what shear we use for our design. This is like a shear force diagram. As you expect, shear is highest, closest to the supports, like those columns. At the columns, if you have a beam loaded on top and supported on the bottom, the load near the column would actually kind of flow downward right into the column. If you have a beam loaded on the top, supported on the bottom, your load from the top of the beam flows down right into a column. You assume you got like these 45-degree shear cracks coming from the face of the column outwards, and they have to be fully cracked. It's a distance of D, right? And over that distance D, all the load just goes right into the column instead of actually being a shear force. It's just a straight compression force into the column. So because of that, and here it'd be D on either side of the column. Here it'd be a distance. D, again, your load's going right there. So we say loads transmitted directly to your support in the compression fan. Kind of looks like a fan, right? And as a result, will not affect the stresses in the stirrups. That cross the crack. Therefore, the shear that we have to design for can be taken at a distance D from the support. So I don't have to design for the peak shear right at those supports. I can move a distance D from the supports. And this is the shear that I need to design for. So I cut off that little peak. Because all of the load is actually transmitted right to the support, and it's not going to affect those stresses. This phenomenon is discussed in 9.4.3.2, which is on page back in my reinforcement requirement stuff. So it's back in chapter 9. There it is, factored shear, required strength. Section 9.4, required strength, page 130. So all the way back at page 130. Required strength, 9.4 is all about how you determine your required strength. For your factored shear, sections between the face of the support and the critical section located D from the face of the support. Shall be permitted for, let's see, where am I? From the face of the support and a critical section located D from the face of the support. For non-pre-stressed beams, beams shall be permitted to be designed for VU at that critical section if A and C are satisfied, A through C. So they say the support reaction in the direction of applied shear introduces compression at the end of the region. Into the end region, loads are applied at a top or near the top of the surface of the beam, and no concentrated load occurs between the face of the beam and the critical section. So this means this is a picture that's also in, right, it's also in the manual. It's down here. This is the critical section. You can go a distance D, and that is the section that you designed for, not here, because this assumes that all this load is putting that part into compression right down into the support. So, let's see. BU can be taken at a distance D from the face of the support only if the support reactions introduces compression in your end region. Loads are applied at or near the top of the beam and no concentrated loads within that distance. at the top, right? If there was a concentrated force right there, that might not actually be too bad, but if it was like right there, then you wouldn't be able to do this. And you can see the load is up at the top. All that force is just putting this in compression. And that's your critical section, where you have your AV over S times D times FYT. That's your shear contribution, and then your VC as well. If you're looking at locations, see this first one, beam loaded on a tension flange. Well, now your load isn't up on the top, it's in the bottom, so your critical section has to be at the face of the support. You can't come out a distance D. Beam column joint, obviously this would all be in compression, so you can go out a distance D from that column face. This one also works. Beam supported by shear. Let's see, the critical section. If beam is supported by a tension force, right? If you're like got this hanging thing right here, now you're in tension, so you can't go out a distance D. You have to take the shear right at that face. Because basically you have to look at where your cracks are coming from, right? The crack could start there. Beam with concentrated load close to the support. Then your critical section again has to be at the face. So critical section means is the section to design for shear BU. Meaning if you had this situation, EDA, you might have to design for a higher shear. You don't get to move it in a little bit where you might have less shear. B and C, you can move it in. All right, your critical sections are there versus at the face. And with that, I will stop here and do another video for a sheared example.